we don't have any knowledge of what determines the probability distribution. So we are going to guess. We are going to assume that this is something that changes as a function of time in a manner that is determined by the first derivative, and higher order derivatives are less important, that it has a part that is kind of independent of fluctuations and is a functional of phi and various derivatives, could be all kinds of things that go over here, and it has some kind of a noise. And we said that anything that I can put over here should possibly be included. So we started writing this. And we said that if I make an expansion, there is no reason a priori why a term that is proportional to phi should be absent, in addition to various gradients and higher order derivatives. And that once such a term is present, you will have a time scale in the problem that depends on microscopics. And if you make your system bigger, that time scale for relaxation does not change. So what are the ways to remove microscopic time scale? One thing was to tune by changing external parameters, etc., to a location where A is 0. But this, I will say, involves tuning and is opposite to what I want, which is generic. A kind of better situation, we said, is obtained when you have a symmetry where your equation, your V of phi, should not depend on where you measure the fluctuations from. In the sense that if I were to add something to it, the answer should not be modified. And so one example is if I'm thinking about some surface height that is growing, the fluctuations in the surface height may not depend on where I measure my height from. And similarly, in these models that Letitia was talking about, if I'm thinking about a solid, and where do I measure these fluctuations in the position of the atoms from, if I were to translate the entire lattice, I will be measuring displacement with respect to another point, but the answer should be independent of that, and that's why the cost of phonons in a solid also is something that is gradient squared rather than displacement squared. And once we have that and convert that to equation of motion, we won't have this term present because we are not going to be able to allow any dependence on phi, and all of this whole series would go away. So both of those mechanisms are mechanisms that exist in equilibrium and we can discuss. So this mechanism is tuning to a critical point. This mechanism is having an underlying continuous symmetry that is broken, like in the solid, hexatic, etc. And then because of the symmetry associated with that, that's so-called the Goldstone mechanism. The modes that you generate from that cannot have a dynamics that involves a term such as this. But since all of those are present in equilibrium and we would like to go off equilibrium, let me introduce yet another mechanism, which is the one that we will be talking about, which is conservation law. So imagine that, for example, I'm thinking about fluctuations in the density, not density, but composition. So let's say that I have a mixture of A and B that are moving with respect to each other. Maybe some places the composition of A is larger, some places the composition of B is larger, so you have composition fluctuations. But if all that happens is that atoms of A and B are exchanging, the total amount of A in the system always remains the same, no matter how the composition is going to change. So in that case, what that means is that I have something like the integral of the quantity that is fluctuating, the integral of composition, for example, that cannot change with time. D by dt of this entire thing has to be 0. Okay? And if d by dt of something is 0, and things are happening locally, so that, say, my A atom does not change positions with the B atom that's a mile away, but only with its neighborhoods, then the variations in phi at each point, so the composition and locally changes because from the neighborhood something comes in or something goes away to the neighborhood. So that means that the change that I have at each location in space is related to what comes in and what comes out, and what comes in and what comes out can be represented as the divergence of some kind of a current. Okay? So the analog of this thing that I had over here, that my motion had a regular part that was independent of noise, the behavior of the average system, if you like, and some fluctuations that eventually cause probabilities. If I have a conservative system, I should have a J that is deterministic, that is the analog of this, and maybe a J that is stochastic. So this is the analog of the noise. And this J, in the same way that V was a function of phi, J should be a function of phi and various gradients. Okay? Now the difference between writing a series for V and writing a series for J is that J is a vector. This V was for our scalar field, a scalar function. So what I need to put here on the right-hand side are vectorial quantities. And again, if I have an isotropic system, the kind of vectorial quantities that I can think of are gradient of phi and gradient of functions of phi and higher order types of derivatives. Okay? So if I were to sort of look at the lowest order term, just to sort of get a feeling for what my theory is, once I have a conservation law, I have on the left-hand side a time derivative of this quantity phi of x and t. And because of the conservation law, you can see I have this difficulty. I cannot write the term a phi because that's not the gradient of any current. So the thing that removes all of these terms is now this other conservation law. Okay? So once I have that, then the lowest order term that I get is going to come from the divergence of this term. So what I will get at the lowest order would be something like a Laplacian operator. So here I would have the diffusion, and there would be all kinds of higher order terms that one has to think about. So based on the ideas of conservation plus locality, I come with this kind of equation. And of course, we have to have some kind of a noise. And this noise is something that has zero average, because all of the averages I put in the component that I call the deterministic part, if they are non-zero. And then I have to write something about its fluctuations. Okay. And again, here I have lots and lots of things that I could play with. And I'm going to always sort of think about things that are generic. And generic means that I don't want to put by hand long-range correlations, etc. I want to eventually have my system where things are only thinking about the local neighborhood to develop long-range correlations. it would be cheating if from right the beginning I put long-range interactions, then I wouldn't be surprised if I get long-range correlation. So for the same reason, I don't want things to know about many times in future, so I put a delta function in t minus t prime. Normally, I would have put here, with the idea of locality, a delta function in x minus x prime, but remember that this has to deal with this divergence that is appearing over here. So because of that, the object that appears here will be a Laplacian of t minus t, x minus x prime. And some coefficient, let's call that coefficient just to be like diffusion 2D. So if I were to take this object and Fourier transform it, so then the Fourier transform is very nice. I have dt of the Fourier transform that depends on Q. And essentially the only thing that Fourier transform does at this level is it converts this to minus mu q squared. Remember that I'm making an expansion, so in principle I could have had additional terms q to the fourth and all kinds of things appearing at the linear level. At long wavelength q goes to 0, this is going to be most important. I have phi tilde of q and t. And then the Fourier transform of the noise, where if I were to Fourier transform that, I will get that the Fourier transform noise has 0 mean. And Fourier transform of that tells me that if I were to look at two different Fourier transformed noise at two distinct wave vectors and two distinct times, I will inherit the delta function in time, and the delta function in space, when we go to Fourier component, becomes 2 pi to the d delta q plus q prime. And then this 2d becomes 2d Laplacian, gives me a q squared in Fourier space. And once more, of course, if it is much easier to write things in Fourier space, I could potentially have higher and higher things. Again, so essentially, if you want to think in terms of the decomposition in Fourier modes, I have thought about one symmetry that I have put in, which is translational symmetry. Things look the same at all locations in space. If you have translational symmetry, then each Fourier mode is going to act independently. So essentially, this is the equation that I would generically write down for the Fourier modes. Each one of them would be acting independently with its own noise and with its own relaxation. And the condition of conservation is that both the relaxation and noise have to start as q squared. Like they can have all kinds of other things. Yes? Yes. Yes. I wouldn't say it is at that order. I would say it's at a higher order. Right? So if you were to sort of look at things and you were to put here a phi type of things, it will be a higher order contribution to average of phi squared. So if you try to solve things systematically, or if you go to, say, MSR formalism, it will appear as a higher order buffer. Okay, square root of phi, which is what you have in, say, extinction processes, etc. The way that I can see how it is higher order is to construct this corresponding field theory in space-time. And if you do that, you will find that that object will appear at third order. But let's, for the time being, not worry about that. But that's certainly an interesting question, which is there's a whole set of different problems where there is extinction going on, in the sense that if phi is 0, you will never generate phi, okay? And if phi is 0 and you will never generate phi, you must put the amplitude of this noise to be proportional to square root of phi or something like that. And for that class of problems, there's a whole level of other things to discuss. You are right, there's some subtleties. Let's leave them for the time being. Okay. So for this class of processes, then solving the linear equation is very easy, because you will have phi tilde of q and t is whatever your relaxation thing is, e to the minus mu q squared t phi tilde q at time 0. And then you will have the integral from 0 to t dt prime e to the minus mu q squared t minus t prime eta tilde of q t prime. So essentially, this relaxation comes from the initial state, but the noise gives kicks, and then you have to think about all of the kicks at different times t prime and propagate them to the time that you are interested in. I'm going to be looking mostly in the limit of t large, and in that limit I can forget about what I start with. It is really the kicks that cause this to move around. It is clear that since the average of noise is 0, the average of this quantity phi tilde is 0. I should have said that along the things that I have assumed is that this noise, I can terminate it at the level of second order. In principle, who said this is a Gaussian noise? You could have higher and higher order terms, but higher and higher order terms are also less important than the variance. It's just like the central limit theorem. As you add more and more things, it's the variance that is left over. All of the other things become less and less important. Although in principle, once you have solved the linear theory, you have to look at the effect of all of these things around the linear theory. So the only thing that is really interesting to calculate is phi tilde of q and t, phi tilde of q prime and t. So I look at the same time, but in the limit of very large t. And so that part has gone away. I have the 0 to t. I have to, since I have 2 of this, I need to double this integral. So I have the t1 prime, the t2 prime. I have e to the minus mu q squared t minus t1 prime minus mu q squared t minus t2 prime. I have the noise of q at t1 prime. I have the noise of q prime at t2 prime. And the average goes and acts on this. Okay? But for this, I can substitute what I have over here. Right? So immediately my double t integral becomes one integral, because I have a delta function that forces these 2 times to be the same. And I should have written a q prime. This delta function forces these 2 q's to be the same. But since I wrote 2 q's out here, I really have to maintain this delta function q plus q prime. It goes outside the integration. I have this magnitude, which was 2dq squared. And then I have the integral. There's one integral that is left, 0 to t dt prime. Because q prime and q are opposite each other, q squared and q prime squared are the same. So I double that, and I will get e to the minus 2 mu q squared t minus t prime. And this is an integral that I can immediately do. The result of this integration gives me a factor of 1 over 2 mu q squared. I will, in principle, get a factor of 1 when I evaluate the integrand at t prime equals to t. I will get 1. When I evaluate it at t prime equals to 0, I will get e to the minus 2 mu q squared t, but I'm in the long time limit, and I'm going to ignore that. Okay? So what do we get? We get 2 pi to the d delta function q plus q prime, and we get 2dq squared divided by 2 mu over q squared, which is d over mu. Okay? So the question that I had in mind, and I should have really stated it before jumping and doing the calculation, was the following. That I started with this equation, and I tried to be as generic as possible. And the generic equation has a relaxation time that is microscopic. I said, I don't like that. I want things to be macroscopic. I need some trick to remove it. And for non-equilibrium system, we said, let's focus on conservation. So by conservation, I remove the time scale so that a mode that has wave number q or wavelength lambda has a time scale that is proportional to lambda squared. So I made relaxation of the mode slower and slower. The next question is, okay, I made things to be scale invariant in time. Are they also scale invariant in space? That is, do I make a correlation between this point and some point that is far away, although everything that I put in was short range? And that's what I'm trying to answer here. Yes? Okay, because when you do the Fourier transform, you will get e to the I q dot x from one of them, and from the other one you get e to the I q prime dot x prime, right? And then I have a delta function x minus x prime, and the delta function x minus x prime sets both of them to be the same. So I end up having to do the integral of e to the I x dot q plus q prime. And integral of e to the I x q plus q prime is a delta of q plus q prime. It is 0 when q and q prime have opposite signs. Okay? So one of them is plus q, the other is minus q. Okay? And indeed, when you are calculating the absolute value squared, you will get 1q, and then you get a minus q. Yes? Only in time. Yes. 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 Okay, so if you like, let's imagine that I have a system that has a maximal lambda, maximal size of it, and I go to times that are longer than lambda L squared. Okay? Fine. Really, the question that I have is much more basic and simple than that, which is that having established that, I ask the question that at this limit of this time having gone to infinity, if I look at one point and some other point, same t but different locations, what are they correlated to each other? And what I have to do is I have to do the back Fourier integral d dq 2 pi to the d, d dq prime 2 pi to the d, and again your question of e to the I q dot x plus I q prime dot x prime is important here, because now I have to write, after Fourier transform, the average of phi tilde of q, phi tilde of q prime, And you can see that according to what I calculated, the phi tilde of q, phi tilde of q prime average has this delta function. So I have to substitute that over here. And it is precisely the delta of q plus q prime that will render this as e to the iq dot x minus x prime. Okay? So what I get is that the answer is this ratio 2dq squared. Note, I should have really made sure to write these things together. This integral gave me 1 over 2 mu q squared. I had a 2dq squared, so the q squared cancel. I get here a d over mu. So the final answer, since the two q's get merged together, is 1q integral. I have e to the iq dot x minus x prime, and the magnitude is independent of q. It is simply d over mu, which means that if I look at what is happening in space after a very long time and ask what's happening, I see that there is no correlation. Okay? So I was able to make things last a very, very long time, but I couldn't entangle the fluctuations at long time. They're completely independent of each other. And the reason for that is that somehow at this level, the equations that I have written, without my having any intention of having put it there, have the symmetry that Jorge has been talking about, which is the fluctuation dissipation condition or the detail balance condition. Okay? So this is kind of implicit in what Jorge has been talking about. There is something called a model B dynamics, which says that suppose you have some kind of field H, some kind of field that is governed by some energy function H of phi. Then you can write down an equation for variation of phi, which is minus the divergence of a current. As long as phi is conserved, I would have to write it like the conserved equations that I had. The current is minus the gradient of the functional derivative of h with respect to phi. And then I have to put divergence of a noise. And actually, maybe I will put here a mu as some kind of mobility that drives the system. And I put the magnitude of the noise here as square root of 2d and call the rest white noise, which is that structure that I had over there. Then the statement is that this kind of symmetry that Jorge has been mentioning, if you have some relationship that is d is mu kt, then once you run this stochastic equation for a very long time, there will be a probability distribution for this field phi that emerges, and that probability distribution is precisely the Boltzmann distribution. Okay? But as Jorge has been emphasizing, you get that only if you have a symmetry. And I did not try to put anything like this by hand in my system. However, when I had done all of these linearization, I really had no choice. I had to put some kind of a constant over here for this, and I had to put some other constant over there. And the ratio of these constants, if you like, defines an effective temperature, so that this probability distribution that I have over here is really the thing that corresponds to integral of phi squared over 2 with some temperature that is related to the ratio of mu and d. But it's the other way around. Okay. And so since essentially you can see this is phi squared, it's completely local. It doesn't, one place doesn't know about anything else. So that seems kind of not very helpful if I'm really interested in things that are long range. And it seems like I have run into a problem. Right, from somewhere, yes. Yes. Exactly, yes, exactly. Yes. Uh, I didn't say anything. Let's imagine your periodic boundary conditions, for example. Okay. Yeah, sure, of course. No, what I'm asking is the simplest way, right? So one can always elaborate. And then the question is what elaboration you want to do, right? So this states the necessity of some elaboration on top of this linear thing that I have done over here, okay? And I suggest you follow up your idea of an elaboration because that's not the elaboration that I'm going to go on. Plus isotropy. Plus isotropy. Okay. So now let's go and see what happens when I remove isotropy. Okay, so this actually was suggested by Greenstein, Lee, and Sachdev around the times that Per Bach was expanding on the idea of self-organized criticality, etc. These guys had something that is along the directions that I'm talking about, which they call generic scale invariance. So again, the key points here is generic. I don't want to be able to tune things. I want to have long-range scale invariance. I don't want things to be local. I don't want to have a correlation length or correlation time. Correlation times we removed by conservation, but we haven't removed the correlation length from the story. Okay, so what they said is all I need to do is to go and make the system anisotropy. Okay. So what we were thinking is about some space over which this thing is fluctuating, in which all directions are equivalent. But let's imagine that for some condition of some gradient or whatever, you call one direction parallel, and the other set of directions, however many they may be, you call them perpendicular, and you don't necessarily treat these two directions on the same footing. Okay? So what does that allow me to do? Again, the whole thing I'm going to assume has translational symmetry, so I can go and write things directly in terms of the Fourier modes. And so in terms of the Fourier modes, I will have dt of phi tilde of q. Now the vector q has both components in the parallel and perpendicular direction. And since the parallel and perpendicular directions I can potentially treat differently, there is no reason for me to write it as minus mu q squared. I can in principle write it as mu parallel q parallel, let's call it mu perpendicular q perpendicular squared plus mu parallel q parallel squared phi tilde of q. Okay? Why not? And then I have my noise, which is a function of q and t. And the correlator of that, eta tilde of q and t, eta tilde of q prime and t prime. Translational invariance, again, forces me to write down a 2 pi to the d delta function in q plus q prime. This is really a requirement of translational invariance. I can't play around with it. I still would put a delta of t minus t prime because I don't want to generate things that are non-local otherwise. But once more, who said that the strength of the noise in the two directions has to be the same? I will have here a d perpendicular, q perpendicular squared, and d parallel, q parallel squared. Okay? So now when I go and do all of the calculations that I have done over here, just go through, except that rather than putting this form, I have to substitute that form. For the relaxation, rather than putting this form, I have to put the form that has the 2 mu's. So you won't be surprised that at the end of the story, if I pick a particular mode and look at its square fluctuations, the square fluctuations, rather than being the ratio of d q squared over mu q squared, where the q squared vanishes, become d pair q pair squared plus d parallel q parallel squared divided by mu pair q pair squared plus mu parallel q parallel squared. Okay? Yes. Dimension minus 1. So this, sure, yes. Okay, you are correct. So this is the q parallel is a 1 component vector. The q perpendicular is a d minus 1 component vector. So if you want me to be precise, okay, I will put this vector, although when I square it, I don't really need to do it. But in this is really the sum of all the d minus 1 components squared. You're right. Okay. So you can see that the q squared drop off only if, so this equilibrium symmetry holds only if d parallel over mu parallel equals to d perpendicular over mu perpendicular. Okay? And as we said, this mu over d is kind of like a temperature. So if you like, this is a 2-temperature problem. I have a different temperature in the parallel and a different temperature in the perpendicular direction. Okay? So now I can't get rid of the ratio of the q's. And so the question is, what are the correlations in real space? So for calculating correlations in real space, phi of x, t, well, we are looking really at very long time, so we might as well drop the t dependence. Also, really, we are looking at objects that are translationally invariant, so one of them I put at 0. Yes? Okay. So in the model B stuff that I erased, temperature is the ratio of mobility and noise, or noise and mobility, and that you immediately see over here. That the eventual thing that I have is in the form of a Boltzmann weight, provided I interpret d over mu as a temperature. So in that sense, I have 1 d over mu in one direction, 1 d over mu in the other direction. If you want to interpret them as temperature, which I don't particularly want to do that, but since people do mention multiple temperatures, why not? Why shouldn't I do that? Yes. Okay. I said that I didn't say it's equilibrium because I never constructed things on the basis of equilibrium. I said in quotation equilibrium symmetry because what I have shown is that without intending, originally I had built in a symmetry that made my final probability distribution like a Boltzmann distribution. So in that sense, this condition, if they are they are equal. So if I had put originally equal, the equal imposes some symmetry in which this Q's fall out. When the Q's fall out, I go back to having this distribution. Uh, okay, so let's call um, no, I don't think so. Let's do. So what I'm saying is that I will have right. So I will have the perpendicular. Let's say I have this condition that d parallel is d perpendicular times mu parallel divided by mu perpendicular. Okay. So then this becomes d perpendicular. I will pull out. I will have q perpendicular squared plus mu parallel over mu perpendicular q parallel squared. In the denominator, I factor out the mu perpendicular. I will have q perpendicular squared plus mu parallel over mu perpendicular q parallel squared. Then I can erase these two. Yeah? Okay. So I wasn't that far off. Okay? So, system has translational invariance. Let's just pick points x and 0 and figure out what we need to do. I have to really do what I had over there. I have to do an inverse Fourier transform, dq 2 pi to the d. I have e to the I q dot x because, or substituting for x minus x prime if you like. And then I have this ratio of d perpendicular q pair plus d parallel q parallel squared divided by mu pair q pair squared plus mu parallel q parallel squared. Okay? Fine. So this does not look like something that gives me a delta function. So let me tell you what it does give you. Just to make the calculation easy, simplify. So I don't need to do that, but it makes life much simpler. We are going to assume that in the mu direction you are symmetric, but in the d direction you are not. So I will use a single mu because that then reduces the denominator to 1 over q squared. Okay. So then the kind of thing that I need to do is Fourier transform of objects that are some component. I will have a q squared. The mu, let's say we've taken out. I have q pair squared plus q parallel is the entire q squared. But then I have here on the numerator either q pair squared or q parallel squared. Let's just generalize it. I usually simplify, but let me generalize and put q alpha q beta, where this could be qx, qy, whatever, including q pair squared or q parallel squared. They're all included in this general tensor, and I have to Fourier transform that entity. Okay? Now I claim that this entity I can get very simply by starting with the Fourier transform of e to the I q dot x divided by q squared, if I can do that and I take a derivative with respect to alpha and derivative with respect to beta, each derivative of x will bring down a factor of iq alpha, iq beta, and I generate this. Okay? Now, in the very, very first lecture, I evaluated this for you. This is the Coulomb integral, right? So what I want to do is to take two derivatives of the Coulomb potential, which we saw that in general dimensions behaves at x to the 2 minus d divided by some surface area factor and a 2 minus d. Doesn't really matter, it's only the power law dependence that is important. If I were to take the first derivative, the derivative, this I can regard as the product of two x's. So this will generate for me one factor of x. In fact, with the power of 2 minus d, that will kill that. So I will just have a 1 over sd here. And I will have, rather than this, I will get x to the power of d. Okay? And when I take one more derivative, I will get 1 over sd. I will get a delta alpha beta magnitude of x to the d, or acting on this, I will get a minus d x alpha x beta x to the power of d plus 2, which is the dipole-dipole interaction that we also saw in the first lecture. So this is the generalized dipole-dipole interaction, which you've also seen in other lectures as Oseen tensor or all kinds of things. It's really two derivatives of the 1 over r potential or whatever the generalization is. Okay? So once I have this, then I can calculate this entity immediately. And what I get for that entity is that my phi of x, phi of 0, this correlation function, is up to this factor of 1 over st, composed of two components, one of them coming from d perpendicular. D perpendicular here will give me x perpendicular squared divided by x to the d minus d x perpendicular squared divided by x to the power of d plus 2, whereby this I just mean the magnitude of the separation. And then I will get a contribution that is proportional to d parallel, which is x parallel squared divided by x to the d minus d x parallel squared divided by x to the power of d plus 2. And I can rewrite this. I think I have rewritten it, so why don't I just look at my notes. I have a 1 over mu in front. Excellent. Yes, thank you. Right, because I have this mu that is factored out between the two of them. Okay? So the final answer is 1 over mu, this factor st. There is a component which is d minus 1 times d pair plus d parallel divided by modulus of x, if you like, to the power of d. And then you have a minus d d pair x pair squared plus d parallel x parallel squared divided by x to the power of d plus 2. Yes, thank you. Because it's a delta function, and here this should be also delta function 1, and dimensionally all of them should be 1 over x to the t. Okay? Yes, indeed, the delta function will give me a d minus 1. Good, thank you. Good, 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 good. So there, it's good that people can catch my errors. All right. So let's just check one thing so that we know that we are not completely off base. If d parallel and d perpendicular are the same, then this becomes d times big D, and here x pair squared plus x parallel squared cancels the extra factor of x squared here, and this becomes minus d times big D. So when the parallel and the perpendicular are the same, there is no correlation for x not equals to 0. There's a delta function that is buried there, right? But generically, you see that all I needed to do was to introduce an isotropy and just follow my nose without making an assumption, and I generate these long-range correlations. If you like, we know exactly what the probability distribution is also in Fourier space, because I have these Gaussian Fourier modes and I know their variances. So why don't I know everything also in real space? The reason is, if I were to sort of think about this and inverting it back to real space, I cannot write it as a local equation. Okay? So in some sense, there is, if you like, an effective Hamiltonian for this system that generates for you these long-range correlations, but it's not a local Hamiltonian. You wouldn't have written it on the basis of gradient expansion. So if you like, that's one consequence in this linear theory of having two temperatures. Sure, because I know that there is a probability distribution in phi tilde of q squared, which is e to the minus this object, right? It's e to the minus d parallel mu per q pair squared plus mu parallel q parallel squared d per q pair squared plus d parallel q parallel squared phi tilde of q squared. So all you need to do is to invert back, and you'll get a quadratic Hamiltonian that describes your phi of x, but it's non-local. I don't see any current. I mean, I did, okay. I don't know where you see the current. Because you are thinking in terms of the perspective of temperatures in real systems. And that's one of the things I don't really like in people using temperatures as effective temperatures for these systems, because all of your intuition is likely to lead you astray. If you like, sure. But I mean, I constructed everything on the assumptions of locality. If, I mean, I would believe that complicated systems that you write down, in my own experience, there is this KPZ equation or whatever, you don't know what the eventual probability distribution is, but it exists. I'm not sure. I think in both cases, or in all cases, you will write down some kind of stochastic dynamics with additional nonlinearities, all kinds of things. There is eventually some outcome for what the Fourier-Planck tells you the probability distribution goes to. Okay. And so that's whether that probability distribution you can calculate by some equating of the effect of noise and effect of relaxation. I have no intuition for that. Yeah. I don't claim that it is there. Mhm. Okay, but even if it exists, it's a kind of hard way of eating, right? Because what my idea is to do things generically and simply. So it may be just like the first case, that there is some symmetry in this problem, but it's not something that is very nice. It's certainly non-local and all kinds of things. But this is a case where you can calculate what the measure is. Okay, so so okay. Would you have guessed it beforehand? Okay. Look. Yes. Right. Okay. Uh, what would not hold? That I would not find an eventual steady state? Okay, so what wouldn't hold? Uh, yeah, certainly I will get all kinds of things by this construction that are different from things that I do in equilibrium. I've already demonstrated that. I've already gotten for you long-range interaction in a system where you wouldn't have expected things on the basis of something else. So it's clear that if I generalize this to more complicated things and more complicated dynamics, I will generate all kinds of things. But in some sense, that's the end of how much I can do. So it's irrelevant as to how much further we can go with this. Yes. I don't think I have seen that connection. I mean, it is certainly true that anisotropy generates for you an additional term that I haven't written. I have implicitly assumed plus minus symmetry, so I don't have the usual advection term. I don't have the IQ term. And the IQ term is another way of taking fluctuations and translating them over long range. Yes. Okay, so exactly, I do have it. That one I can't say. And that's what Jorge had said before, why not, right? So you have to show me once I write things generically, why not? Okay. All right? So, Why did I want to do all of this when my talks have all been about fluctuation-induced forces? Well, the thing was that fluctuation-induced forces became nice and interesting when I had long-range correlations. So what I have shown you is in a system based on conservation law and anisotropy alone, I can generate these long-range correlations. So the question is, can I generate a fluctuation-induced force also? Okay. So there's a number of questions pertaining to that. The most important one, I don't know whether we'll get to it together, is what does it mean to create a force from this non-equilibrium system? But the easier part is the following. Let's go and do the Casimir geometry. So let's imagine that I put this field theory that we discussed in between two plates that are separated by distance h. So my phi of x and t is living here. And because maybe I want to think in terms of fluids and densities, or maybe because things become simpler, I will impose not the Dirichlet boundary condition, but the Neumann boundary condition. dz phi, if this is the z direction, is 0 at h, and dz phi is 0 at 0. Okay? Yes? Okay, so the question was, writing these dynamical equations for a field phi, what is the kind of minimal conditions that I should write down in order to generate correlations that are long-ranged? And the first thing that I said is that if there is a microscopic time, that determines relaxation. I have to remove that, and I said that I will remove that by having a conservation law. So that removed the time. And then I said, well, does it generate spatial correlations? And we found that in the isotropic system it doesn't, but just going to anisotropy is sufficient to generate that. So it is, in some sense, non-generic because it's not applicable to isotropic system, but it's not such a big deal, if you like. You can have a current going through the system or whatever. All you need is to privilege one direction, and then you should generically have this. Okay? All right, so my field phi is fluctuating in between these two slabs and has 0 gradients at the two surfaces. Okay? So what I want to do is to calculate what phi of x squared is, the variance of this quantity that is fluctuating, and how it is modified by the fact that I put it in a finite interval of size h. Okay? So I said at the beginning, one of the things that at some point will come and bite me is putting the factors of v or not for Fourier transform. So let me be precise here. If I discretize all of my Fourier modes, the relationship between phi of x squared and phi tilde of q squared involves a factor of 1 over volume. And in this system, I'm going to replace the volume with h times the area, and my q vectors is going to be discretized in this direction in terms of multiples of n pi over h, whereas in this direction I'm going to treat it as a continuum. Okay? Which means that in the other direction I will replace the sum over q with an integral which involves the density of state, and density of state has a factor of area, which gets rid of this, and I will get an integral ddq perpendicular, actually dd minus 1q perpendicular, divided by 2 pi to the d minus 1. I have a sum over n, and this is again another thing to remember here, which is that since I have both Neumann conditions, my n pi over h's will start at n equals to 0, not at n equals to 1. I have the constant mode as well. And so then I put phi tilde of q squared. Phi tilde of q squared, I have it over there. It is d perpendicular q perpendicular squared that I'm treating as a continuum. I have d parallel n pi over h squared. In the denominator, I said I choose the same mu, so let's essentially take that mu out here. I have q perpendicular squared plus q parallel squared, which is really just q, well, not really, because it's q perpendicular squared plus n pi over h squared. Yes? You could do all combinations. Yeah. It's just sort of sticking with the Casimir geometry that we were dealing with before. Okay? I'm going to slightly manipulate this so that it becomes simple. So I will add n plus n pi over h squared to this so that it cancels against that, but then that means I have to subtract it over here. It's the same thing, right? Okay. So this part I can get rid of because it just gives me a usual thing that I would have for systems that are one temperature, if you like. I will get a q squared over q squared. If you kind of look at it carefully, you mean that once you have a constant, the constant amounts to summing over all total number of modes. So you will actually get a factor of density for the first term. So that's something that is a constant. The point is the second term up to this coefficient of d parallel minus d perpendicular is one of the things that we calculated, right? We did this sum and integral at least for the special cases of d equals to 2 and d equals to 3. These were our thermal Casimir forces. So we have done those integrals. So the outcome of this calculation is going to be a bunch of terms that we had before, well, sorry, bunch of terms that are reasonable and normally would be there, but because of the structure that involves this discretization, I will get a component that is proportional to the ratio d parallel minus d perpendicular, which is how much I have broken this symmetry divided by mu. There is a factor, I have to be careful because there are factors of h over here. There will be a factor of 1 over h to whatever dimension that I have over here, and some Casimir-like amplitude that I have to put over here. That would be the result of essentially repeating the type of calculation that we had done before. Okay? So, fine. There is, all I want to sort of conclude up to here is that once I have generated in this system that was non-equilibrium, had anisotropy, conservation, long-range correlations, not surprisingly, once you put boundaries, things start to feel the effect of boundaries. Because you have long-range correlations, you feel the effect of boundaries, which was really the important ingredient that you wanted to have for creating Casimir forces. That boundaries modify things over long distances so that this boundary knows about that other boundary. Okay? The other thing to remember is that all of the correlations that we've calculated really have this fall of 1 over x to the d, and that also shows up in this 1 over h to the d. Also, everything is clearly related to this breaking of the fluctuation dissipation condition, all of correlations, all of the knowledge, etc., is buried over here. Okay? Yes? I haven't. Okay, that is going to be the $1,000,000 question. Okay, so all I have said is that this phi squared has something that kind of looks like what we had calculated before for Casimir's. But it's also non-universal because it certainly depends on the ratio of these quantities. And also its sign can be positive or negative depending on which d is larger than the other one. Okay? But now the $1,000,000 question. So when I had equilibrium, what I did eventually, if you think about it, is that I was generating some kind of a probability distribution for something, for phi, for x1 minus x2, for let's call it for phi with the boundaries. And then I was saying, oh, I'm going to regard that as a Boltzmann weight, so I take its log and I multiply by minus kt, and I call that some kind of an interaction that depends on h. And once I have the interaction that depends on h, I would calculate its derivative and it would be force. And so the idea was that somehow my fluctuating quantity was exhibiting some kind of probability distribution that I could interpret as the Boltzmann weight of some environment with which it was in equilibrium. That environment had a temperature. I could convert that into an energy, and everything was set. Now, in what I have told you, I have constructed this thing just on the basis of hand waving. And where is the energy? Where is the force? I need an additional input beyond what I have given you. I just haven't given you enough in order to calculate forces, so I have to introduce another assumption. The problem is not that I don't have a probability distribution. The problem is that I don't have a KT. Okay? Essentially, we are going to introduce a KT. It comes under the heading of assumption of local equilibrium. Okay. So let's imagine that our phi measures non-equilibrium fluctuation, but it is close enough to some system that I can identify as reasonable equilibrium. Just to give you an example and something that we will be working on, let's imagine that we have something that is flowing through a pipe, and if I set the velocity to go to 0 so that the non-equilibrium condition disappears, essentially this object, this fluid, will come to rest, and I can sort of look at it. And when it is come to rest, I can define some quantity that is like a force. So for example, maybe I can define a pressure in equilibrium, and let's say that that pressure is a function of density and some other quantities that I can identify in this system. Okay? Now, let's say that once I started to move this thing, I find that locally what I can measure is density fluctuations. So there is some average density that I had before, plus hopefully sufficiently small fluctuations around it. And these fluctuations are caused by the non-equilibrium thing that you are doing. There is no underlying equilibrium theory whose dynamics maybe is the driving force of these fluctuations. But there is a close-by system for which once you know the average density, then you know what the pressure is. So the assumption of local equilibrium is that at any instant of time, you can associate a instantaneous pressure, which is really the pressure that you would have had in equilibrium, except that your density has been changed by this fluctuating quantity. And there may be other quantities. Since I wrote the theory for a scalar variable, that's really the only thing that I have. Okay? So that's how I sort of introduce via some system for which I know the pressure, something like this. I should tell you that maybe this thing you also know from something else. So in one of the things that we did with Alex Solon, our starting system was not a gas in equilibrium where we had pressure as a function of density, for example, but it was an active system. So there was some active system on the computer that Alex Solon simulated, and for that system, he could just empirically go and calculate what pressure was as a function of the density of things that you put there. So somehow externally, he had this formula. Then on top of that, you add some current, and there's some additional non-equilibrium fluctuations due to current, and the hope is that this is still valid. Okay? So then, at least for small enough fluctuation, you start to expand this. You will have this. Then you would have the first derivative, p prime, evaluated at rho bar phi. And then you have p double prime over 2 evaluated at rho bar phi squared. And then you say, okay, if I average over now the fluctuations, this entity will disappear. And that's why I was calculating phi squared. That somehow I can put the phi squared that I calculated over here in here and get a non-equilibrium correction to what equilibrium pressure is arising from non-equilibrium fluctuations. Now this is an assumption. I should say that it's a hard thing to completely believe. I wouldn't believe it myself. One reason I have difficulty believing it is that in equilibrium, you have, like in this room, there is a pressure as a function of density. Nobody worries about worries about the existence of pressure in equilibrium as a function of density. We may worry whether this room is in equilibrium. That's another story. But even in equilibrium, if you look at any volume, the density is fluctuating. You are not justified to do this in equilibrium. You don't correct the equation of state by the fluctuations in density. It's just not done, right? So there is some reason to question this, and so I let you mull the validity of this over dinner, and we can discuss whether it's valid or not tomorrow.
But I'm still not understanding why there's absolutely no length scale in fluctuation, because you have the noise is you have a noise which is a current. Yes. So there should be like a tiny length scale, because if you're looking at one given t,
Right.
so you have an average 0 concentration, let's say, but you have small currents,
Okay. So if
and
you
this
look
should
at
give
it
a negative
correctly,
term. Yeah?
this phi of x prime has a delta function of x minus x
Okay,
prime.
so this
So
is
you
the
have
delta.
to unpack that. You have to say that this delta function is really that small distance that you are talking about, but it's no more than that.
Okay, because the noise is